This video is going to run through the Earth's interior PowerPoint. So how the videos will work is, I'll run through the PowerPoint. I might not go as in depth on every slide. And so it still is in your best interest to download the PowerPoint and run it in slideshow mode, because there's some animation sometimes and different things that I want you to see. So it'll walk you through that. So it's in your best interest to certainly do that. This is kind of the Reader's Digest version, but let's kind of go through and see what we got going on here. So what we've got here is we want to learn about the Earth's interior because it has significant consequences to what's happening on the surface of the Earth. So certainly we'll want to talk about some plate tectonic stuff, which is related to volcanoes and earthquakes and everything like that. So some basics are that we can differentiate the Earth in a couple different ways. Probably the most common and the way that you've probably learned in high school is that the Earth is composed of the crust, the mantle, and the core. And that is true. And in general, those divisions are based on composition. So the argument is that the crust is different composition from the mantle. So let's say we were going to drill into the Earth. We drilled down through the crust, which was made of a certain material, and we hit a boundary where all of a sudden there's something new, a new composition material. So that boundary is between the crust and the mantle. And you can see from this diagram here, the crust is relatively thin. It's this kind of darker gray line here that's extremely thin. And then we'd hit the mantle. So the mantle is actually all the way from right below the crust. In this case, there are two different types of crust. So we have the oceanic crust, which tends to be fairly thin, and the continental crust, which is a little thicker. But once we get to the base of either of these types of crusts, we will have the mantle, and that's from that point all the way down to the core. And so for the most part, the mantle is composed of similar material. And just like our example from the surface, if we kept drilling, we'll eventually come to some contact where we have some different material. And so that's where the core comes into play, and that's the boundary between the mantle and the core. Now, the reason that you have these two different cores named outer and inner is not necessarily because the composition is different, but because the phase in which they exist is different. The outer core is actually a liquid, and so the inner core is a solid. What we'll find that as we go deeper in the Earth, it definitely gets hotter. And that has the potential to cause the materials inside the Earth as you go deeper to change from a solid to a liquid. We kind of know that from experiences on the surface of the Earth, right? We heat things up, they change from a solid to a liquid. So why is the mantle not a liquid? It's not a liquid because of pressure. So as we go deeper in the Earth, not only does the temperature rise, but so does the amount of pressure being applied to the material. And you can think of pressure, at least increased pressure, as trying to keep the material from changing from a solid to a liquid. Very generally, if we heat something up, the molecules start to move apart, right? Break some bonds and they kind of separate. And the farther apart they get, then the more chances they're a liquid. They get really far apart, they're a gas. If they're really close together, they're a solid. So that's very simplistic, but it's kind of true. And so as we go down in the Earth, the heat is want to move those molecules apart, but the pressure is crushing them together. And so for the most part, we would argue that based on the type of material in the mantle, pressure wins the battle, and our mantle stays mostly solid. But at the boundary between the mantle and the outer core, temperature starts to win the battle. And so because it's made of different material, the core is, and it has different properties, at this temperature and pressure, this material that makes up the core is a liquid. But as we keep driving toward the center of the Earth, pressure is still rising, so is temperature, and we reach some conditions at the center here where the pressure is so great that it overrides the high temperature, and now it's a solid. And so we have this compositional way, crust, mantle, core, and of course there's some nuances to how the core behaves or looks, I guess, because of the temperature and pressures that are involved as we go down into the Earth. Now that's not the only way that we can look at dividing up the Earth. We also can look at how the material behaves. And so for that, we kind of want to look near the surface. And what we see in this diagram here is you have both of the different crusts that I just talked about. Ocean crust, thinner. Continental crust, thicker. They are made of different material, but they're still considered the crust because at their base, they do have the same boundary, right? So this transition from ocean crust to mantle is the same as continental crust to mantle. So that material that separates those is the same beneath each. Now, when we're talking about composition, we would say there's the crust, has different thicknesses, but below it, boom, that's a compositional boundary, and we have mantle below that. But for behavior, we're going to argue that the crust behaves in a brittle fashion. It is rigid, it is colder, and so when we apply pressure to it, it can fracture and break. Kind of like what we experience in everyday life. If we took a rock and hit it with a hammer, it would break, crack, fracture, right? Well, the upper mantle is also fairly cold, and it behaves the same way as the crust. And so we are going to take the crust, and it doesn't matter which kind, and a portion of the mantle here, this upper part, and we're going to combine it together and use the term lithosphere to describe the way that this part of the Earth behaves. It is colder, and it is much more rigid, and it behaves in a brittle fashion. So this lithosphere breaks under pressure. Beneath that, we have what's called the asthenosphere. Now we've reached this boundary where even though we have the same composition at this boundary right here, where the lithosphere and asthenosphere touch, they behave different. And so this one breaks and is cold, this one is warmer, and here's the weird part. This part of the mantle has the ability to flow or move over geologic time. It is not a liquid though. It's not water, it's not magma or running around inside the Earth. The whole part isn't magma. That's kind of a misconception. It's kind of like, think of maybe like wax or like silly putty, something like that, where if you took a piece of silly putty or clay and you applied pressure to it, slowly it wouldn't break. It would kind of move. It would deform in such a way that it would allow it to flow or move. This is kind of how the asthenosphere behaves. And so that's why we're separating it out from the parts above it, which is the lithosphere. So these are important because when we talk about earthquakes and we talk about plate tectonics, the plate and the part that breaks is just this lithosphere part. So we can get earthquakes anywhere in this lithosphere because it is brittle. We don't get earthquakes down here because it doesn't break. And so this is another way that we can define these different zones. And so lithosphere, asthenosphere are the two kind of main names that you'll want to remember, and they are based on how the material is behaving or the properties of that material. All right, so just to clarify, because some of the diagrams might not have been helpful, but it's the mantle that's given us the grief, right? The crust is brittle, is always brittle, but the mantle is broken into a couple different parts based on its behavior. So the upper part, that's the brittle part of the mantle, that is included in the term lithosphere. So crust and upper mantle make the lithosphere. Below that, we have this very ductile or it's kind of soft material that's allowed to move called the asthenosphere. And then the rest of the mantle is kind of termed the mesosphere, and it's just even weirder. It kind of flows like the asthenosphere, but it's not as much because the pressure is higher. And so for us in this class, the main thing I want you to remember is lithosphere and asthenosphere. Those are the two terms that I want you to remember and what parts of the Earth they consist of. Okay, so here's the deal. So how do we know all this? So how do I know there's these different boundaries? There's compositional boundaries, there's behavioral boundaries or property boundaries. Well, of course, we drill. We drill into the earth, and the deeper we drill, we get some samples, and we can kind of figure out what's going on there. Now, the problem is we can't drill very deep. So certainly we haven't drilled through the earth. And if we look at how deep we have drilled or dug, we can see that it really isn't very deep. Now, it depends on where we drill or dig, because remember in that first diagram we showed that the thickness of the oceanic crust is pretty thin compared to the continental crust. So maybe about 7,000 meters deep here, maybe, right? And 30,000 for the continent. So we have some mines that are pretty deep and some oil wells. The problem with these really deep wells is they're on land. And so you can see that we never drilled through the continental crust. And if we make it to the ocean, because we have to go through miles of water first and then into the the oceanic crust, it's challenging to drill very deep there. So we have never, to this date, drilled through the crust into the mantle. And it's even crazier if we think about, trying to hit the core mantle boundary, right? Because that's super deep. Now, there's been some attempts to do that, and you can kind of look at those links to read more about that. But we've never sampled them. So then how the heck do we know what's down there? Well, we have to go to a hazard, right? A geologic disaster, basically, of earthquakes. Earthquakes actually give us information about the earth. So they're bad, of course, because they cause damage, but they give us lots of information. And that is because whenever there's an earthquake, there are these waves of energy that move through the earth. And based on the material they're moving through, the properties of the material affects how they move. It affects the speed, how fast they move, and it affects their direction, right? So when they cross different boundaries, they can change direction, and we can use tools like seismometers to record these energy waves, and they can help us see into the earth, kind of like remote sensing. Think about like a CAT scan of your body, right? So someone's not actually drilling or cutting into your body to see what's happening. They're using these images to look into your body. They're using some science. And so these seismic waves, which we'll talk a lot about when we talk about earthquakes, but really briefly, I just want to give you a quick tutorial about different types of waves. Now, there's a lot that we get with earthquakes, but in particular, there's these two types of body waves called P waves and S waves that are generated when an earthquake occurs. Now, why do we care? Well, the one thing, let me go back really fast here. Sorry about that. Is that number one, these are fast. The P wave, it's the first wave that arrives at our seismic station. Why? Because it's very fast. And the way it transmits the energy, it can move through anything, solids and liquids. So if there's an earthquake somewhere, we can record it on our seismic station. If it's really big, I can actually record it all the way from the other side of the earth. It would travel the entire depth through the earth and come out on the other side, and I could record that on my seismometer. The other wave that we see is called the S wave or shear wave, and that transmits energy a little different, so it's a little slower, but the key here is that it can't move through liquids, only solids. That gives us some information about the interior of the earth. And so we talked about the speeds being different of these waves. Their speeds are also different depending on the material and their direction, and so when we look at waves like this, we can have a direction that the wave energy is generated. If there's a different material here, we get some reflection of the energy waves. We get some refraction of the energy waves. These can be recorded, and the time it takes to get to our station can be calculated. That tells me something about where this new boundary is, right? Because I can figure out how long it took to get from my earthquake to my seismic station. I don't want to get into the gory details because we don't need to, but in general, this is what's going on to help us understand the interior of the earth without actually sampling it. We also talked about it'll penetrate through the different material, but it'll change direction. And so then we can record that in another seismic station, because if you're unaware, we have thousands upon thousands of seismic stations now all around the world. And so we get lots of data, and we can use all that to figure out what's happening. So one of the big first boundaries that was discovered was in 1909 by Moho, and so it's sometimes called the Moho, is the boundary between the crust and the mantle, and it was discovered by looking at arrival times of these different wave patterns that we see when earthquakes occur. So they use the data to figure that out, and that's where they determined that, hey, there's a compositional change here. The material's different, and so the waves behave differently in there. They're faster in the mantle, or slower in the mantle, faster in the crust, and so that gave us some indication there was a boundary down there, which is called the Moho, because of this gentleman who discovered it. Now, I want to show you something else that would give you some confidence maybe that we understand what's happening inside the Earth. And so here's an example of an earthquake that has happened up here where the star is, and then the paths of the energy waves would move through the Earth. If it's big enough, it can be recorded on the other side. Now remember, we said P waves travel through solids and liquids, and the story we're telling you is that there is a liquid core, at least part of it. Well, the P waves can go right through there, and so I should be able to get those on the other side. Now this other one is a little better. This is the S wave. Now remember, we said those cannot go through a liquid. So if I have an earthquake up here where the star is, and I have a seismic station on the other side of the Earth, for some reason, I don't see any S waves show up at my seismic station. What does that tell me? It tells me that somewhere inside the Earth, those waves ran into a liquid, and they weren't able to propagate through. Now, based on this weird, what we call shadow zone, where we see no S waves, we can determine the size of that liquid kind of sphere that's inside the Earth. Because look, if this was a lot smaller, the boundary was deeper in the Earth, then my shadow zone would be smaller, because these P waves would come down here like that, and my S waves would come down here, and my shadow zone would be smaller. If the boundary was closer to the surface, which means the sphere is larger, then my shadow zone would be larger. So just this little example told me that there was a liquid material at depth, and it actually told me the size of it based on this shadow zone. And so this is how we get some of our data to determine what's happening inside the Earth. And remember, there are not only lots of seismometers around the world, but there are thousands upon thousands of earthquakes that occur. Now, all of them aren't enormous that can give us information for the entire Earth, but certainly there are enough to give us some information about the different types of materials, different boundaries, what's happening inside the Earth. So we feel pretty confident that we understand what's happening inside the Earth based on properties of these waves. And so we know there's compositional changes and behavioral changes because we have lots of data like that. So that's how earthquakes are helping us see inside the Earth. And that's kind of just the basics. Once again, when we get to earthquakes themselves, we'll talk a little more about this stuff. But I just want to give you some insight into how we can figure out what's happening inside the Earth without actually drilling in there. All right. How else can we look inside the Earth? Well, we can actually look at some gravity. And so we can measure gravity pretty accurately. And so we know that gravity is related to mass and distance. And so we can use that fact to figure out what's happening inside the Earth without drilling for things that are relatively close to the surface. And so what we could see is that because distance matters, right? So the farther away an object is, then the weaker the gravity would be. But of course, the mass is big, then of course there'll be a larger impact on gravity. So we can use those factors to kind of determine what's at depth without drilling. So if we have something that's very massive, then we'd get a change in gravity and increase. If it's really far, really close, that would affect gravity. And so we have these little gravimeters that would measure the gravity over a certain area, and the change in the measure of gravity tells me something. If I have objects down here at depth, this is very massive, and so it would have a larger pull on gravity, and so my gravimeter would show a change, an increase. Here's empty space, and so that's certainly less massive, and so my gravimeter would show a change where there'd be less of a gravitational pull. And then I'd have something as a proxy that would say this is what it normally should be. So that can give me some information at depth. So we can use that to help us understand and find sometimes deposits that are useful, but even cave systems that might be detrimental to people on the surface if there's a collapse feature there. And so we can check for these what are called anomalies by using these instruments to go over different parts of the Earth. And so it can start to give us a picture of what's happening inside the Earth, because different rocks have different masses, and so they're going to show a change as my gravimeter moves over that area. In combination with some earthquake data, we can get a fairly good picture of what happens inside the Earth without drilling. So that can do structural stuff. Sometimes, there's old earthquakes that we can discover, or old faults, or certain deposits that we can discover that can be useful if we need to mine them or things like that. Okay, a couple more points about our lovely Earth and what's going on inside, and then we'll wrap it up. So we do have a magnetic field that's being generated by our planet, and that is related to the composition of the core. So the core is thought to be iron and nickel composition, and because we have a liquid outer core and a solid inner core, the motion of those particles, those iron and nickel particles around the solid iron and nickel, can generate a magnetic field. And so that, of course, protects us from some radiation that's, being bombarded. We're being bombarded by the sun. It also, of course, helps us navigate. We use that for that, and it helps animals navigate. And so there are these force lines that are generated that we can not see visually, but we can measure. And so it, like I said, tells us which way our compass is aligned with these lines of force. And so the story right now is that because this movement of liquid iron around a solid iron core is generating this field that we see. Of course, it's very deep and it's very challenging, but of course, if we kind of replicate this in an experiment, we can see that by doing this, even though there's some chaos in the motion here, it's very turbulent, we still get some directional flow which would generate this magnetic field. And there's evidence to support that process can generate a magnetic field. So we have that going on there. Now, how's that important besides the fact that it kind of helps us? Well, certainly it gives us some information about the history of the Earth and how it's changed over time. Now, the thing that we want to also be aware of is we have a magnetic North Pole, and is not the same as the geographic North Pole, right? So the geographic is just based on an imaginary line that runs through the planet based on the spin of the planet, and so like a top. And so that's kind of arbitrary. It's based on the spin, and there it is. Well, the magnetic pole is not in the same spot, and it can move around over geologic time. Not only can it move around over geologic time, but we have evidence to suggest that the magnetic field has flipped in the geologic past. So magnetic north today might not have been magnetic north in the past. So if we had a compass and, 200 million years ago, it would point to the South Pole instead of the North Pole. And so how do we know that that is true? Well, the rocks themselves can record the orientation of the magnetic field. I know it's crazy, but when molten rock cools, it has a lot of these molten rocks have a lot of iron in them. And they can form certain iron minerals, and those iron minerals, called magnetite, will actually line up relative to the magnetic field that is currently happening when that rock cools. We can use that to say, hey, because we can see it today, right? We have lava, it cools, we take a sample, take it back to the lab, measure the orientation of these minerals. They're all aligned with the current magnetic field. But when we find older rocks, we see that they're actually flipped, pointing in the other direction. And so what this helped us with was, number one, to understand that we had this reverse in polarity, that things have changed over geologic time, so that was helpful. But it also helped us with some clues for plate tectonics, which is a huge theory for geology. And so we'll talk about that in the next module. But because the age and the direction of the rocks, the direction of the minerals alignment can be recorded and discovered, it kind of told us how new crust was created over geologic time. And so I guess the big push for this module is just to understand that the magnetic field exists, how it's generated, and the fact that it can change over geologic time. We don't know the implications of that, right? Is it fast? Is it slow? Does it cause mass extinctions when that happens? Or is it, not a big deal? So that's something that we're still trying to puzzle out. Okay. So not too much about that. And then I think I'm gonna just have you look at this here, so you can play this video. It's embedded in the PowerPoint. Basically, just one more way we can see inside the Earth. By locating the epicenters of earthquakes, we can determine some information about what's happening. I'll show you this again in future modules. But basically, this is a map view, and it's going to plot locations of earthquakes on the surface of the Earth. And then this one is a 3D-ish model, and it's going to show you the locations of earthquakes inside the Earth. And what you'll see is that a pattern is formed here, and it tells us something about what's happening inside the Earth. It tells us something about how the brittle part of the plates interact with each other and what happens when they collide or pull apart or things like that. And so, like I said, we'll talk about that in the next module when we talk about plate tectonics. But I just wanted to cover kind of a lot or most of the tools that we use to look inside the Earth without actually sampling. And of course, tell you a little bit about the magnetic field and the interior stuff. All right. So it sounds like a lot of stuff, and this was a long video. But the basics, of course, here are you should understand compositions that make up the planet. You should understand the behavioral differences, the terms we introduced, how we figured out what's happening inside the Earth with seismic waves, at least in general. Understand about the fact that there is a magnetic field and the potential understanding of how it's generated and the fact that that can be altered over time. And that there's some other tools like gravimeters that can also give us information about what's happening inside the Earth. Okay. That was long and potentially, hopefully, not too boring. Okay, so take a look through the PowerPoint if you still need to, and visit some of the links if you want some more information. Otherwise, this is the bulk of the information that you'll be quizzed on in the lecture quiz.